And now we move on to Diogo Belloni, who is giving a talk about a new model for the formation and evolution of close magnetic white dwarf binaries. Diogo, the stage is yours.
So first of all, I would like to thank the organizers for the opportunity to be here talking about a very nice recent model we developed to explain the closed binaries hosting magnetic white dwarfs. So basically the systems that Stephen and Anna talked about, but considering that they are magnetic, they host a magnetic white dwarf. So thanks for that. And before addressing the model itself, I will just summarize the observational properties of the systems. So as you know, we can separate them between the detached population and the semi-detached population. The detached population so far corresponds to the prepolars and AR skull. And the semi-detached population corresponds to the magnetic CDs, mainly polars and intermediate polars. With respect to the fraction of the systems, with respect to the entire population, we have very different fractions. In the detached population, we have that less than 1–2% of them are magnetic. And on the other hand, in the CDs, we have that 34% of the CDs are magnetic, and this seems very problematic if you imagine that this detached population will become the CDs. If the detached magnetic systems will become the magnetic CDs, so these fractions they are not consistent with this evolutionary picture. About the field strength in these populations, the fields are usually stronger than 10 megagauss, but we also have a population with weaker magnetic fields in CVs, the so-called intermediate polars. And the systems, they are expected to be old, but for the detached population, we can measure more easily the age and the temperature of the white dwarf, and they are usually older than 1 gigayears. So this is an old population. Unfortunately, no scenario, no model proposed so far for the origin of magnetic white dwarfs can explain these observational properties. And that's what motivated us to develop this model. To precisely explain these discrepancies, these apparent discrepancies. And this model is based or inspired by an earlier work by Isern et al. 2017 in a paper that they claim that a dynamo similar to that operating in planets and low mass stars and low mass primary sequence stars, the same dynamo mechanism could also operate in white dwarfs. And the reason for that is that a white dwarf, when it cools down, and this white dwarf will eventually start to crystallize. So this crystallization process will happen. And this happens when the temperature is sufficiently low. And so this crystallization process provides a very nice configuration which corresponds to a solid core surrounded by a liquid convective mantle. So if the white dwarf is rapidly rotating, which means that if its spin period is sufficiently short, a dynamo can be produced in this convective region. And this dynamo will lead to magnetic fields. So a required condition is that we need a white dwarf with short spin period, and maybe this could be a problem because from observations we know that white dwarfs are slow rotators. Here's a plot showing the spin period against the mass, and then we can see that most white dwarfs have spin periods longer than 1 day, and this could be even months or years. So for this kind of spin periods, we expect only non-saturated dynamos leading to weak fields. So we could, in principle, not explain this 10 megagauss or even stronger magnetic fields in this population. But this is not a real problem if we consider that the white dwarf can spin out, and the white dwarf would spin out because it's in the case it accretes angular momentum, so the white dwarf can spin out. But how this could happen if the white dwarf is accreting mass? So if the white dwarf is accreting mass, it's also accreting angular momentum. So the white dwarf can spin up. And this is the key ingredient of this model we developed. And it's nicely described in a paper recently accepted for publication led by Matthias and me. And this implies that in closed binaries, we have the magnetic field generation during the CV phase. Sorry, it became really noisy here. Just move a bit. Coming back. So the key ingredient of this model to allow the strong magnetic field generation in closed binaries during the CD phase, precisely the phase in which the white dwarf is accreting mass and in turn accreting angular momentum and in turn is spinning up. So the required conditions to form these strong fields, again, we need a crystallizing white dwarf and a rapidly rotating white dwarf. And the rapidly rotating, I mean spin periods of order of 1 minute, even shorter. And a crystallizing white dwarf implies a white dwarf older than 1 to 3 gigayears. And so now I'll go into more details about this model, how we convert a non-magnetic binary to a magnetic binary. So what happens before the magnetic field is generated is basically what we have just listened from Stephen and Anna. We have a common envelope phase, and then this common envelope phase leads to a closed binary. But this closed binary now hosts a slowly rotating non-magnetic white dwarf. Then because of the angular momentum loss, the orbit shrinks, and during this process, the white dwarf may eventually start to crystallize. And also eventually the secondary field is Roche lobe, and then we have the onset of the CD phase. We have the onset of mass transfer. So here we don't have anything new actually from what Stephen and Anna told us. The only thing we are considering here is, as additional, is that we consider that the white dwarf can crystallize. And also we take into account the rotation of the white dwarf. So during the CD phase, the white dwarf is accreting mass, accreting angular momentum, and then the white dwarf is spin up. So the spin period decrease until it's very short. And when this happens, we have the conditions for the dynamo, these conditions are met. So we have a solid core surrounded by a liquid convective mantle, and this white dwarf is rotating quite fast. So we can form a strong magnetic field. So now we are going to assume that this strong magnetic field it's really strong and can connect with the secondary magnetosphere. So if this happens, we will have synchronizing force because the donor in a CD is synchronized with the orbit. So this means that the donor, the secondary, is spinning much slower than the white dwarf. And provided that both magnetospheres are connected, we have the synchronizing force. So the effect of the synchronizing force is to spin down the white dwarf And because of angular momentum has to be conserved, this angular momentum is transferred from the white dwarf to the orbit. So at this point, we have a competition between orbital angular momentum gain because of the synchronizing torque versus the orbital angular momentum loss because of magnetic braking and or emission of gravitational waves. So the effect of the angular momentum gain is to expand the orbit, and the effect of the orbital angular momentum loss is to shrink the orbit. So if the orbital angular momentum gain wins this battle, we will have a short phase, a short detached phase, because the orbit will expand. So, so whether this binary can become detached or not, this will depend on how fast the white dwarf was rotating when the magnetic field was generated. How strong is this magnetic field at which orbital period this happens, and also the efficiency of angular momentum loss. So considering that this orbital angular momentum gain wins this battle, we have a detached phase. And this detached phase is precisely how we explain this, the detached population of closed binaries hosting magnetic white dwarfs. Precisely how we explain AR-STO and prepolars. So in the beginning of this process of synchronization, because of the synchronizing torque, in the beginning, the torque is very strong, so the binary detaches. But the time scale of the synchronization is longer than this detachment. And so here we're talking about 5, 10, 20 mega years. So in the beginning, we have a detached binary hosting a pulsar-like white dwarf, very a rapidly rotating white dwarf. And that's precisely what we see in AR-STO. After this synchronization process is finished, after these 10, 20 mega years, so the whole binary is synchronized. So the white dwarf, the secondary, and the orbit, they all rotate at the same frequency. And so we don't have anymore the angular momentum gain because of the synchronizing torque. We only have the orbital angular momentum loss. So the binary will eventually reach the CV configuration again because of this angular momentum loss. But before becoming a CV, now hosting a magnetic white dwarf, it will become a prepolar, which are synchronized systems hosting us almost filling in which the secondary almost fills the Roche. And so after the prepolar, we have the polar, precisely the second CV phase during the evolution of this closed binary. And so I would like to emphasize once again that according to this model, the detached population, which means AR-STO and prepolars, they are not pre-CVs, they are not progenitors of cataclysmic variables per se, but they are actually post-non-magnetic CVs. And this might be surprising or difficult to imagine, but this is entirely consistent with observations. So if we have a look at the distribution of the detached population in this plane, white dwarf mass and white dwarf temperature, and here we have in gray the non-magnetic systems, and in red the prepolars and AR-STO in blue. We can see two things here. The first one is that the magnetic systems, they are on average much older, much cooler than the non-magnetic counterpart. And they are consistent with having crystallizing core. And to know that, we use this line here, which represents the onset of crystallization. So the temperature, the critical temperature as a function of the mass. So within the uncertainties, we can claim that this is consistent with having crystallizing core. The other thing we see is that the magnetics are more massive than the non-magnetics. So as Anna told us, the mass distribution of CDs have on average this mass 0.8. So we can also conclude that it makes entirely sense that these systems have been CDs in the past. And there is an additional sort of evidence, let's say, or at least of agreement, is when we compare the Roche-Low filling factor. And here we have the age of the white dwarf against the Roche-Low filling factor. And then we can see that the magnetic systems, they have on average larger Roche-Low filling factors. And this is consistent with them having a previous phase, a previous CV phase, a previous phase of mass transfer. So after describing this model and also showing how consistent it is with observations, I will show how a close binary evolves through these states, let's say. And to do that, we incorporated into the MESA code this spin up of the white dwarf, the crystallization, also the condition for synchronization, and also the synchronizing torque. And but we have to arbitrarily set a magnetic field for this system because we need to develop the theory to give the field strength. So what I'm going to show is the evolution of a closed binary in this plane, orbital period against the spin period. So after this non-magnetic closed binary is formed, because of angular momentum loss, it shrinks. And during the process, the white dwarf eventually starts to crystallize. And they have a slowly rotating white dwarf. So at some point, we have the onset of mass transfer. Then the white dwarf quickly is spin up and keeps decreasing the spin period until a moment it's sufficiently short, then the magnetic field is generated. Then at this point, the binary becomes detached. And in the beginning of the synchronization, we have AR skull. And in the end of the synchronization, we have a prepolar. Then this prepolar will quickly evolve into a polar. So we have the second CD phase, but now CD hosting a strongly magnetized white dwarf. So this is a summary of the model, and this video was produced with one track from the MESA that we changed it to incorporate all these things. So I'm close to finish. I'll just summarize the observational properties that this model can explain. The first one is the absence of magnetic white dwarfs among young, close detached binaries. Also, the high incidence of magnetism in CDs is 30–40%. The low incidence of magnetism in close detached binaries, this 1–2%. Because of the time scale here for this phase, so we don't expect too many. The existence of AR skull, we can also explain the system that's in the beginning of the synchronization process, and the relative frequency of magnetic and non-magnetic CVs. So thank you very much. And I'll be happy to answer any questions you might have. And sorry for the noisy in the middle of the talk.
Thank you very much, Diogo. Questions? So James was first.
Hi, Diogo. Thanks for a really interesting talk. I thought this was a really fun idea. I have a question about the magnetic field strengths. So the polars rotate slower, but they have stronger magnetic fields. If the magnetic field strength is related to a dynamo in the white dwarf, might you expect the opposite trend, that polars spin slower and therefore should have lower magnetic field strengths than the intermediate polars?
Not actually, because let's go here. So if you check this plot, we have, let's say, at this point here, when magnetic field is generated, we have already, let's say, 30 megagauss or 60 megagauss. So we have the synchronizing torque. So in principle, we could see this 60 megagauss systems in any of these points here in this track. And so the polar is not, I mean, so the fact that we have stronger fields in polar, it's not necessarily because, at least not according to this model, it's not because it's rotating slower. It's because it's the end of the process. I'm not sure if I answered well. So let's say
that the field, once it's generated, it will stay for a year, for gigayears. So it doesn't decay quickly. So if you once generated a strong field, then it will be maintained. That's shown in the ESAN paper, 2017.
Even if there's an active dynamo, I mean, there's still an ongoing dynamo.
Yeah, it depends on, that's true. That's something we don't know, how fast the dynamo is generating the field, how fast the field appears, and then what happens if the dynamo is still working and the field is generated with the field. But the field doesn't decay quickly. So when there is a strong field, I think it should still be there.
Okay, thanks.
Tom was next, I think.
So I just lowered my hand. I think my question's essentially been answered. It was the same area.
Okay. Ken?
Hi, thanks, Diogo. My question was about what accretion, the regular CV phase does to the crystallization, because heat is being diffusing in from the accreted material, and I'm wondering if that liquefies the crystallized core and what that would do to the structure.
If it is heating because of the accretion.
That's right, yeah.
Okay. Well, I have a slide here just to show a plot with illustrators. Okay, so here is the core temperature, and then we have a white dwarf in red and a CV in blue. So you can see, because of this heating of the core, at some point the white dwarf stops to cool down, so it remains the same temperature basically. So if the white dwarf is not crystallizing before the onset of mass transfer, then likely it will not crystallize during the CV phase. So the CV will remain non-magnetic. At least from what we know so far, that's what we expect. But if the white dwarf is partially crystallized and then the CV phase starts, this is precisely this case black here. We can see that indeed the core temperature increase, and eventually it will start to melt the core. But the time scale should be long, and I don't know what's the impact on this on the magnetic field, because according to our model, given this time scale here, the magnetic field should be generated before it affects the core. So I don't know what would happen after the core is being melted. I don't. Matthias, do you know what? After we form the magnetic field and then the core is being melted?
Yeah, I think that's the same thing. The magnetic field will stay. But if the core is melted before the magnetic field can be generated, then the dynamo doesn't work. That's the way I see it. Does that answer your question, Ken?
Yeah, thank you.
So, Solon.
Hi, I think so many people. Do you hear me?
Yes.
Yeah. Okay. I guess there are so many questions that I should ask something quick at the very end in your summary in the last line. You had the relative abundance or relative frequency of magnetic and non-magnetic cataclysmic variables. How do you explain it in the context of this model? That's I guess, right? That's the idea.
Yeah, I also have a slide here for that. Here. Because we have basically two situations in which the white dwarf will remain non-magnetic. The first one we briefly discussed about is this: if the white dwarf is not crystallizing before the CV phase, then likely this heating, because of the accretion, will not allow the core the core to crystallize. So this CV will remain non-magnetic. And the other situation is when we have a very, a large fraction of this white dwarf is already crystallized, because you need a large convective region to allow strong magnetic field. If we don't have this, if the white dwarf is 80–90% crystallized, then we cannot form a strong field as well. And so, depending on several parameters, we can have a large fraction of these non-magnetic case. Also, we can have a lot of magnetic case, depending on, and the main parameters are these ones: the common envelope efficiency, what is the limit of this crystallized mass we need. For example, do we need to have 1% of the core crystallized, 10% of the core crystallized to allow this dynamo to efficiently work? So this is an uncertainty which will change the fraction of magnetic and non-magnetic CVs.
Okay.
I think that answered the question.
Yeah. Thank you for the detailed explanation. Thanks.
We have one more question. Time for one more question, Dean.
Hey, so thanks. A very interesting scenario. So I just wanted to ask. So the previous sort of reason for the magnetic CVs to be more prevalent than in magnetic and isolated white dwarfs was that they evolve more slowly, right? So the angular momentum loss is different for magnetic CVs compared to non-magnetic CVs. So do you have a difference in your prescriptions for angular momentum loss for the non-magnetic versus magnetic CVs, or how is that different in your model?
I can show you one. Sorry. Here's a plot comparing the secondary mass against the orbital period. Maybe this one first. So for the non-magnetic case, we have, let's say, the full magnetic breaking prescription. So here at the onset of the CV phase, the donor mass decrease, and then when it becomes fully convective, we have this so-called gap phase, this so-called detached phase. If we incorporate the magnetic field, and if this magnetic field is strong enough to connect with the secondary magnetosphere, part of this wind leading to magnetic braking will not leave the system, will be trapped because of the connection between the magnetosphere. So we have a reduction of the magnetic braking.
Right. That was the pre-existing model. Yes.
Yes. So we incorporate this. So as soon as the magnetic field is generated, we have this because we have the connection. So we have the synchronizing port. So we already assume that this magnetic braking is reduced. But if the CD is formed below the gap, so we don't have this difference. Then we also have the same angular momentum, but this affects those CDs with above the gap.
Okay, thank you.
Okay. So I think we have to move on.